of all, let me thanks, the organizer, Randy, Marcus. That's really fantastic to be here at this workshop. And I think I have really to make a very special thanks because I'm learning a lot. And I have to make a little disclaimer. So the last time I worked with fermions in the lattice were 15 years ago for my PhD. And I should really say that it's very hard to catch up all what fantastic physics was going on, in the last more than a decade, let's put it this way. And also, it's a pleasure to be at ITAMP. CERN is a fantastic place to be here and discuss physics. So in my talk, I would like to present a little bit a different system with respect to the one we learned in the last talk. And so the special feature, or one of the special features, is that the atom I'm considering, they have a very large magnetic dipole moment, okay? So they are highly dipolar, and the dipole-dipole interaction have a magnetic character. And now I want to focus, so the atomic species I'm using is erbium, and I would like to focus on the Fermi gases. What I would like to try to do now today is give you a bit of a sense of what is the difference between short-range interacting fermions and long-range interacting fermions. So this is the outline of my talk, and it's a very standard outline. So we go from one spin state, so we are studying indistinguishable fermions, identical fermions. Then we move to a two-spin state, spin mixture, and then we search Feshbach resonance and interspin Feshbach resonance. And then I will also discuss some very new results which are done in collaboration with Anna Maria Rei and Bihui Tsui, which is also ITAMP postdoc fellow. And so in this type of outline, there is also natural, let's say, chain of order in terms of interaction. So if you think about short-range fermions, let's say alkali fermions, lithium, potassium, so what you have is that in one spin state, the system is non-interacting, okay? Because of the Wigner threshold law, short-range potential, collision in odd partial waves, so the elastic cross-section goes to 0. So at the end, you can get a Fermi gas, which is really an ideal one with no interaction. Then in a two-spin mixer, you can create weakly interacting. Then you can search for a Feshbach resonance, and then you go in the strongly interacting regime. And then when you study spin dynamics in lattice-confined fermions, a lot of the spin dynamics observed and discussed is driven by the super-exchange interaction. Now, what happens if we change from short-range fermions to dipolar fermions? So the first things that you have to notice is that even in a single spin state, so identical fermions, also in this case, the fermions are interacting, okay? Why? It seems a little bit counterintuitive, and the reason is that now the interaction is long range. From a scattering point of view, the Wigner threshold law changes and allows you also at 0 temperature to have the p-wave collision. And then the weak interaction I'm speaking about for indistinguishable fermions has a purely dipolar character. Now, if from one spin state I prepare two spin states, I go again to a weakly interacting Fermi system in which I start to have two sources of independent interaction. One is the contact interaction, let's say the short range that we know very well, and the other source of interaction is the dipolar. Then we can go to the interspecies. We can search for Feshbach resonance. So in erbium, dysprosium, in this lanthanide, there is tons of resonance, as you will see, so that's not a big problem to find one. And there one can maybe create a strongly interacting Fermi mixture. And the question is, with the very complex interaction and Feshbach spectrum of erbium, can you create a stable strongly interacting Fermi gas, and what the dipolar interaction will bring in, okay? Where the strong interaction means strong in the short range, so the contact interaction is very large, it's Feshbach resonance. And then when we speak about spin dynamics, so there you have to account for the role of the dipolar exchange interaction. This is a direct exchange contribution. It's a spin-dependent interaction. It's a direct one, do not require any virtual state. Okay, so let's just very briefly look at this first part. And of course, now you have a weakly interacting dipolar gas. The dipolar interaction, you can write it, is basically depending on the magnetic moment. So it's kind of somehow easy to understand and having under control. And so the first impact is, of course, in the few body physics. As I told you, the elastic collisional rate between identical fermions is not zero at zero temperature. Okay? Rather, these saturate at some constant value. And then this is an opportunity, okay, to study collisional dynamics. And this has been done, for example, for inelastic collisional rate in polar molecule. And my focus here is about the elastic collision. Because if you have enough high collisional rate, you can use it to directly evaporative cool identical fermions. You don't need any sympathetic cooling, any mixture. You can just exactly have the same protocol for boson and fermions, and you rely on this dipolar interaction. Moreover, which is kind of amazing, the elastic collisional rate is a constant, but also acquire a universal value. Very simple. And the elastic cross-section actually depends on the so-called dipolar length, which is nothing else of something depending on the magnetic moment and on the mass. And so this universal, let's say, scaling have been so predicted explicitly, so let's say this equation, by John Kander and Tickner back in 2009. So we used this idea, and based on this, we actually demonstrated that this rate that we get only due to dipolar interaction between identical fermions is large enough to be very efficient in evaporative cooling. Okay? We don't need any other interaction. And so we could produce in a very straightforward way, just by evaporative cooling, via dipolar scattering, let's say a very cold Fermi gas on the order of 0.11 of the Fermi temperature, and also, which I don't have time to explain you, this gives you an opportunity to produce extremely dense Fermi gas. I mean, this density, it's kind of amazing with respect to the usual density you can achieve. So it's very stable, we don't see any losses, it's very dense and very cold. And this is the impact on the few body physics. Of course, you might ask what is the impact on the many body physics. Now, for fermions, that's much more, let's say, tricky, because the fermions store a lot of kinetic energy, no? So as they distribute in momentum space. There is a Fermi surface, which is a sphere, no, in alkali atom, and they store a lot of kinetic energy. So the dipolar interaction, which I'm speaking about, is small with respect to the kinetic energy stored in the Fermi sphere. However, what we were able to show in our system is that even if small the dipolar interaction, they already affect the shape of the Fermi sea. From a sphere, it can become an ellipsoid. And so this is, you have the Fermi surface, which now get a deformation due to dipole-dipole interaction. Why in this direction? Because the dipole is attractive for dipole oriented in this eye and repulsive in the other. And so we could prove by mapping the momentum distribution, I mean, really simply out of an harmonic trap. So we could prove the Fermi surface deformation. We can see that the deformation rotates with the orientation of the dipole that you can easily do with magnetic field. And then, of course, we show that the deformation can go to zero if you increase the temperature, or that if you increase the dipole-dipole interaction, which for us means increasing the density, so you can also increase the deformation of the Fermi surface. But then, after this first study, let's say a few years, so the study we have done with the dipolar fermions, we were ready to start the next step. So from a single spin state, let's go to a two-spin state, where now you have short-range and long-range interaction. Okay, and so this was our, let's say, mission. So to try to prepare this type of system, and indeed I want to tell you something very special. of erbium, of the lanthanide, which is not directly really related to the magnetic moment and the dipolar character. It's more that these lanthanide atoms are multi-electron atoms. So they have many valence electrons, okay? Not only this, but the valence electrons around the core are in a very anisotropic orbit. That means that the quantum number in the system are all very large, the orbital momentum quantum number. So as a result, erbium is realizing a system in which in the ground state, the spin state is really gigantic. So indeed, is a spin 19-half system, meaning that you have 20 spin states in the ground state. And now you can play around and you can ask yourself, okay, so can I populate just one single spin state? Can I do mixtures? So this is all, let's say, a new playground for us in the experiment. So in the first set of measurements, which I will show you, I will just focus on the two lower spin states, so the ground state, so the absolute Zeeman ground state, and the next one. And I created two spin state mixture, let's say. And okay, so how to create a spin mixture? Now this is maybe technical, but it's also kind of funny somehow, because in alkali, in lithium, you know very well how to create a spin mixture. So you simply use the quadratic Zeeman effect, so you produce your Fermi gas somewhere, then you go to a magnetic field value where the quadratic Zeeman effect is large enough, and then you can populate the spin mixture, you can create the spin mixture. So the path, it's very easy for us. So we produce at very low magnetic field the Fermi gas. And then you see this is the quadratic Zeeman effect. And if we go to, for example, 30 Gauss, already we have 20 kilohertz. OK, we are fine. The Zeeman, quadratic Zeeman effect is large enough. So, I mean, that's kind of the things we always learn. And maybe it's promising. However, there is a little problem with this atom. And those are the Feshbach resonance. Okay, so if I go from this is absolutely not in scale. There are much more than this. We have a density. No, I will show you. We have a density of 30 resonance per Gauss. Okay, so if I now let's have a look really on the data. And this is just fake stuff, and then I was bored to copy and paste this line too many times. But now let's focus from 0 to 2 Gauss, and let's see the Feshbach resonance in a single spin state. Single. I don't even need to have another one. Okay, and so this is the real Feshbach scan from 0 to 2 Gauss in an optical dipole trap. So that's a problem. Indeed, if we then prepare our atom in a dipole trap and we just ramp the magnetic field, so what we get is a thermal gas with kind of useless for what we want to do. Okay, we want to have a cold Fermi gas. So then we were inspired by molecule experiment, and what we decided to do is to then prepare our atom in a 3D optical lattice, deep enough that you have only single occupation in every lattice side. So that means there cannot be really two-body collision. And so with this lattice protection shielding, so this is a 3D lattice, okay, just plotted in one direction. So we have a collisional shielding, so they kind of, the resonance are transparent because you have single occupancy, and you can go at the desired magnetic field and then do your spin preparation, and life is good. Then you melt the lattice, and this is what you have. We do heat up the system, yes, because we start with the Fermi gas at 0.1 TF, and ramping up the lattice actually is the things that heat up the most, and here we have 0.3 TF, still fine. I'm happy, okay? And here we can all do the physics of a spin mixer into a dipolar, into an optical dipole trap. And so we can prepare all the atom in the lower spin state, all the atom in the higher spin state, and we can also produce 50-50 mixer or whatever population imbalance we want to create. And now let's go one step further. We want to study Feshbach resonance between spin mixer and see if there is a broad Feshbach resonance that we can use for BC-BCS physics, as it has been beautifully done with alkali atom. So this is now a very, so zoom in of the spectrum. So This is milligauss, not Gauss. I just want to, okay? So this is a really very small window of magnetic field. So one spin state, you see some very narrow resonance. Then you can put the atom in the other spin state, and you see also, I mean, very narrow resonance, the yellow one for the yellow atom. And then when you do a 50-50 mixture, you see, of course, single species resonance, but also you start to see the emergence of interspin resonance. And one in particular, this one, which might in absolute number be narrow for you, but actually for us is pretty broad, okay? And so we wanted to focus here and to measure the scattering lengths along this Feshbach resonance. We again use a very powerful technique, because you have to know that nobody can predict the scattering lengths of lanthanide at the moment. So the scattering theory model are completely out of reach, really, of being quantitative, because it's a too complex system with many molecular potential playing a role, okay? So instead of singlet and triplet, you have, for example, 48 Gerade Bohr-Oppenheimer potential. Just to give you a sense of numbers. So then what we have to do our work as experimentalists and try our best to measure the scattering lengths. And for this, we again use the lattice, the 3D lattice, as a tool, and we measure basically the on-site interaction in a Mott insulator state. And then from this, and taking account of also the on-site dipolar interaction, we can really map out the scattering lengths, very beautiful, along this resonance. So we have a resonance. Can we use it? Can we have a stable system? And so now this is a very promising result, because now very nearby the Feshbach resonance at a scattering length of a minus 1,500, so we see a lifetime of the spin mixture very high. So this is in second. I mean, the lifetime is in the order of 800 milliseconds here. So it's a long-lived dipolar mixture, Fermi mixture. So it's a very promising result, and then we can map out and get the, let's say, collisional rate along all this resonance, and we see that actually in the BCS side, I mean, the lifetime can be in the order of, let's say, 1 second, okay? So this is very promising, and also, I mean, if you look at the paper in 2004 about potassium-40, I mean, they have really a very similar plot, and also the strength of the decay, it's very similar, okay? So all this is promising, and so, I mean, we need to do some step forward before being able to study fermionic pairing and BCS crossover, and our step will be now we need to cool further, because as I said, all this preparation brings you to 0.33 F. We think it will be better to be a little bit colder before starting a pairing study. But also, I mean, I want to trigger theorists, because as you know, there is a deformed Fermi surface. We show you this, and this effect is not accounted in the few theory I know, at least, for BCS crossover with dipolar interaction. And an isotropic Fermi surface means also an isotropic Fermi pairing. Okay? No, in this one would be 2 spin components, and you can have also an imbalance in the dipolarity, imbalance in the deformation of the Fermi surface. This is, I think, a case not really. This one is a resonance for 2-component fermions. Let's say more in the spirit of potassium and lithium experiment. Each of the components have a deformed Fermi surface. This deformation is a little bit different. So you have an imbalance in deformation. And you can create then a pair, you can imagine at delta k equals 0, but also delta k may be different from 0. And so this is not really completely accounted in the theory, which I know. Maybe I'm wrong. Okay, but now, so we have not yet cooled down further the fermions. This is in our to-do list. We were so excited by having 20 spin state. Let's do something with this 20 spin state. And this brings me to the last part of the talk, because indeed, in this 20 spin state, while working and trying to prepare the spin mixer, we also learn how to prepare really, in a selective way, all the atoms in any of the spin state we want. So we can initialize the system having all the atoms in one of these spin states, only one. Okay? And then for us, we said, okay, but this seems to be a very nice playground to do spin physics in a lattice. Okay? And this is the final part of my talk, where I have to say, okay, again, 15 years I'm not working with a lattice, so if I'm not very precise, please tell me. Okay, so let's go on. And now we have a lattice, okay? And we want to first initialize all the atoms in one MF state, and then to see how spin excitation propagate in the lattice. We don't have a microscope, okay? So we have only global observable. We cannot locally probe entropy and this type of things. Of course, there are fantastic work in spin lattice physics. I mean, NV center, polar molecule, trapped ion, Rydberg atom. But this is now a work with this erbium magnet. And all this work have been done in collaboration with Anna Maria Rey and Biu Itsu, and it was very great source of inspiration for us, and also Manfred Mark, which is here, is really the leading person for all the experiments I'm telling you now. Okay. So this is now the Hamiltonian we would like to study, to realize, and to probe. I mean, this is an Hamiltonian which have this off-site dipolar interaction. I mean, since the interaction is long range, now the dipoles on different lattice sides can see each other. So it's nearest neighbor interaction, okay? And so this is not, let's say, triggering any dynamics. The dynamics is more in this spin exchange term, which has also a dipolar character, okay? And in this case, it's a direct term. The spin exchange interaction is a magnetization conserving. And what it's doing is that the atoms are not moving, as you know, but just the spin degree of freedom can move, okay, as a spin excitation due to the dipolar interaction. And now there is the additional term which I want really to highlight for experimentalists because it's, I think it's convenient, is that we also have a quadratic term, okay, which is given usually by the Zeeman effect, quadratic Zeeman effect. So it's proportional to, let's say, mf squared. But in reality, by changing the quadratic effect, we can actually put, here you see it's 3 spin state as an example, and you have an energy mismatch. So this is out of resonance, so this, the magnetization cannot change. I mean, you cannot have spin excitation because there is an energy mismatch. But now, what you can do, using the quadratic Zeeman effect and the tensorial light shift, which is special of lanthanide atom, what you can do, you can actually reduce the mismatch and put these two states completely on resonance. And in this way, you can initialize your dynamics. Another interesting thing is that since, I mean, in principle, to have this type of things, what I would need to have 0 quadratic Zeeman effect, which means 0 magnetic field, which is very hard. Or, I mean, like in rubidium, you need to have a sweet spot to work. In this case, the light helps us, and we can tune very fast the on-resonance, off-resonance of the spin excitation. And so this is what we do. Now we are off resonance. When I, let's say, put my quadratic term on in such a way that the states are on resonance, some dynamics start, and you have a propagation of spin excitation into the system. That's what we want to study, and this is what we study. This is the off-resonant case. Here you see that we prepare all the atoms in the second to last state. So this is the ground state, and this is the next one, 17.5. We prepare all our atoms here in a 3D lattice, and we see very long lifetime. This is a scale. This is 2 seconds. Okay? And now, when we put on resonance, we see that the atoms are kind of not moving. The tunneling is pretty low, and so we see that the magnetization, so that the spin excitation start to, let's say, arise. Okay, of course, I mean, the mean field prediction is completely out of what we see. It's really this term. Now, let's go a little bit on. Okay, the magnetization is conserving in this measurement. And if we go a little bit on, the question is, are we now probing this Hamiltonian? Okay? is it the right description to our system? And so then, I mean, here's where really we started the collaboration with Bihui and Anna Maria. And so, and they consider this Hamiltonian simulated using let's say, the generalized, the discrete, truncated Wigner approximation, which is actually pretty powerful because, I mean, our system is large. We have a lot of atoms. So exact diagonalization you cannot do with such a big, large size system. And so, but this technique developed by Anna Maria and Bihui, it's kind of very strong. And then what they did, they simulated our case for the feeling that we think we have. And so, and now you see, this is, okay, what do you see? So he's now agreeing. Do we have something missing? Is the model of this truncated Wigner approximation not working very well? I mean, somehow it gives you the order of magnitude of the spin dynamics, but you see, especially at long time, 100 milliseconds, a very clear mismatch, okay? And now we were puzzling and discussing a lot with Anna Maria, and what we realized is that actually, yes, something is missing, okay? And what is missing in our Hamiltonian is another, let's say, spin exchange term, and actually is the super exchange. So what we needed to add is a super exchange term in our description. So you now have, you see, you have direct exchange interaction due to the dipolar interaction and virtual exchange interaction given by the super exchange. These two terms can be all competing against each other and slowing down the old dynamics, for example. Or even you can design a situation in which they, let's say, help each other to fast the dynamics. And so now, by including this, so we see really a very nice agreement between the theory and the experiment. Not only a short range, but also, I mean, at 100 milliseconds, which is pretty amazing. This is not a fit, okay? It's really a theory accounting for our system. There is one parameter which is left free. And it's the fact that we don't know the contact interaction for each spin-state combination. We just know for one spin-state combination, but we know something about the molecular potential of erbium, and so we allow this contact interaction to spread a little bit, okay? And this is the only free parameters. And then going further, what we could see, since we have so many spin states and we can initialize at whatever MF we want, we thought, okay, so let's have a look at this flip-flop term, I mean, the exchange term. And so this is have a dependence on the MF like a square. It's a quadratic dependence on the MF. So we said, can we probe in our system this type of dependence? Really, and then by preparing one, initialize all the atom here, then initialize all the atom here, all the atom here, all the atom here, and this is what we did. This is let's say let's say spin dynamics for different initial spin state, okay. And then from this, we can extract, let's say, a decay rate. Let's focus on the excited state, so on the initial state decay. And so, and this is, let's say, the figure that we have as a function of the different spin states that we have probed. And so it's kind of, let's say, a quadratic dependence. And now if we put the theory from Anna Maria without super exchange, so you see that it, of course, captured the quadratic, but, I mean, the strength is completely, I mean, quantitatively, there is not a good, qualitatively, yes, but quantitatively not. But then, if we use the full theory with super exchange and dipolar exchange interaction, we see an extremely nice agreement between the theory and the experiment. That, given the complexity of this system, for me was really, I mean, a fantastic news. I mean, also unexpected. And then, I mean, so the on-site have dipolar part, and is about kilohertz, is few kilohertz. Okay, now then, I mean, in the theory, we don't have the microscope, we cannot access the Rényi entropy, and in the theory, you see, I mean, the 17 alpha is the slower, I mean, show the slower dynamics, and then here you have the highest one, and then they could probe how the Rényi entropy, let's say, or calculate how the Rayleigh entropy actually increase in our system, and you see a very different increase with respect to the initial spin state. I want to say, for this calculation, you have to account all the 20 spin states, so the full spin space. Or, Anna Maria, I think this is also pretty remarkable. And then, okay, now we have this Hamiltonian, and the other dependence that we want to study now, it's this angle dependence. Okay? And so in our case, it's easy. We have a dipole in a lattice, and we can orient very easily with magnetic field, change the angle as we want. And so we probe at the angle dependence here. I want just to make a little comment, is that the super exchange interaction, this one, is depending on the nearest neighbors, just the next one. Okay? While in the case of dipolar exchange interaction, also the diagonal term play a role. Okay? So geometrically, let's say the angle dependence should be different if you consider both terms or just one. So, and this is our result. I mean, that's again the data as a function of, let's say, the orientation of the dipole with respect to the lattice. And here you see that, again, it fits very well with the full theory, which is the solid one. And with the theory only accounting from dipole-dipole, you see there is a shift of the minimum. And we have to explore more this, but we think it's really due to a geometrical argument that, yes? Yeah, we have a measurement. I don't have the plot. We have a measurement as a function of a few lattice steps, and we see how indeed the dynamics change as a function of the lattice step. Yes. We are, so there is an upper bound of how small we can do the tunneling, so how deep can be, which is given by the fiber we have. But we do see a dependence. So now the tunneling is 10 Hertz. So it's already pretty low. It's 10 Hertz for a recoil of 20 recoil. So it's pretty deep. Okay, so it's a small effect indeed. And we see that the dynamics, the speed of the dynamics change by changing the lattice step. Yes. However, I mean, the theory of Anna Maria, it's more a theory for very large lattice steps. So at some point, if we reduce too much, we can even not compare with the theory, let's say, completely, because then you have real tunneling as well. But we can increase. We went to 25 recoil, from 20 to 25, which is our maximum, and we do see a difference there. And, okay, and then, let's say, is... kind of almost the end of my talk. I just want to show you some feature regarding spin dynamics for future experiment, which is a feature of how fast we can control the spin dynamics. By using this tensorial light shift that put the state on resonance, out of resonance, indeed, it's certainly one direction to explore more deeply, because now it's just an example of the spin population, so how it evolved in time. And now imagine that at this point we put light on, which put a shift. Okay, so we get with the light on very quickly, we put the state out of resonance, and we indeed see very quickly that we stop the spin dynamic. Okay, this is a tool we will explore in the future. For the moment, I have only this plot to show you, and yes, and then you can exactly change the resonant condition, I mean, with and without light. Okay, so with this, that's for the moment all what we can say about dipolar gas in a lattice, and there is for sure a lot to understand, and the microscope will help, but we don't have it. And let me just flash the other two investigations we have in the lab. That's just this. And one is we have studied this, the excitation, the appearance of a quasi-particle, new type of quasi-particle, this Roton quasi-particle in dipolar gas. And now we are really able to map out the spectrum of the collective excitation, let's say from the phononic regime to the rotonic regime, and really see this quadratic dependence at very large momentum. And then in a new experiment, so we were able to produce a dipolar quantum mix, mixing now for the first time erbium and dysprosium. We have double Bose-Einstein condensate and Bose-Fermi mixer, really deeply quantum degenerate. And we are playing around to try to understand the interaction and the phase diagram, let's say phase separation or not of this system. With this, let me thank, let's say this is the team which have done the experiment in the lab. And here, I mean, if you want, there are some additional recent results. And so really the key player in the spin physics, it's really Manfred. And of course, with the help and inspiration and work of Anna Maria and Biui. With this, I mean, I want to thank you and to show you we also enjoy life. And also a little bit I want to say that we have a very interesting postdoc opening in the group and also one PhD opening. So with this, I want to thank you.
What do you mean you also enjoy life? When you laugh, but I have a more serious question. When you were talking about spin exchange and super exchange, I was also kind of surprised, like Eugene's question, the super exchange is playing such an important role. So I was going to ask the same question if you can change the lattice depth. Yeah. And then I also realized in the 3D lattice, we have seen, using light tensorial shift to cancel the quadratic magnetic shift. The light shift is inhomogeneous throughout the lattice. Is it possible that as you're trying to compensate for the quadratic Zeeman effect, there's only certain area of your lattice is actually compensated such that your lattice filling fraction is actually smaller than what you initially thought. And that could turn off the spin exchange.
Yeah, I mean, we indeed, the first thing we thought is that maybe, so we didn't thought immediately that we would have super exchange. We thought maybe it's only dipolar exchange, but with lower filling factor. And
like the resonance is being not homogeneous across the whole lattice.
Yeah, I mean, but the tensorial light shift in this case is given by the lattice light itself.
Yeah, so that's
okay.
That's inhomogeneous.
Yeah, but it's, I mean, in our case, it's I mean, it's not very dramatic. It's a very, let's say, very smooth. But to answer your question, we have now studied the number of atoms, the loss of atom. We have computed, because of course we don't have a microscope, so the occupation. We think that we have something in between 0.706 filling factor for this experiment. And now if we just account for dipolar interaction, we would have to decrease enormously in the filling, and we can have at short time a good agreement when we put a filling of 0.3, so completely unrealistic. But then at long time is not fitting at all. You can just take this t squared, the first part of the dynamics, but then it's completely out. And then we said, okay, the filling is unrealistic. I mean, we don't have, so we would have to decrease a lot just to capture the initial part, but the long time dynamics is completely out.
Then will allow us to explore the light inhomogeneity effects, perhaps.
Yes, we can do this. This I think we can do. It's something, but as I said, I mean, we have pretty big beam, okay. So and of 200 micrometer. So the lattice beam, and we kind of calculated what will be the let's say the Gaussian envelope, and we believe that this is a kind of a very small. Also, the tensorial light shift is not gigantic. We have also to say. So it's at these wavelengths, depend on the wavelengths. At these wavelengths of 532 is something like 5% of the total polarizability, the scalar one. Yeah, we include a part. Yeah. No, 50 hertz in Kirby. No. So a Bij is a 30 hertz or something like this. Yeah. Without it's 18.
It's, so, no, without S plus 0.3.
Oh, okay.
So that's why it's so important to have super exchange.
Okay, thanks.
So I had a question, but this is more on the uniform gas. So one is the comment I made to you. I think, what is your plan? You can do this angle, right, for the dipole. So this is for bosons. It'd be nice to see this beautiful experiment where on the protons would actually there be a proton instability as a function of the dipolar angle. That'd be nice to see, and I think you can do it, right?
Yeah, we can do it.
That'd be very nice. Our work and a few other people's work showed that. The other question I had was on the dipolar fermions, but again, for the uniform case, for a while there was this prediction by theorists who were doing RPA type calculations that there would be a phase separation. And the Monte Carlo calculations didn't find it. What is the current, do you know what the current status is?
The phase separation between...
So you'd have sort of a uniform bulk phase and then some phase which would be sort of polarized in some direction.
I don't know about what you are.
That was a big question in literature for a while. Brun, for example, one of the...
The dipole-dipole interactions are a little bit weaker, so maybe you have to go,
So you remember this work,
yes,
right?
so there is the two, I think you have the superfluid phase when they are aligned, and
Right.
when they are repulsive, depending on the angle, you have the phase separation.
But then...
But you mean polar on physics, or?
No, for example, in the same, if you have a quantity lattice and you have the pancakes,
Right.
you are going to look at the phase diagram in the pancakes, and
Yeah.
now depending on the tipping
Yeah.
angle, look at the attraction or repulsion,
Yeah.
but you have significant repulsion compared to the interfactor.
This you can have phase separation. Now, that's not our regime, by the way. Yeah.
So that's not the regime. Okay.
No, that's
Yeah,
not.
because that was a big controversy. The Monte Carlo calculations did not find it either yet.
Yeah.
Okay, Carlos?
So I have two quick questions. So the first one would be, how big is the covariance distortion that you have?
Of the Fermi surface. Yes, these are deformation. I mean, it's about, let's say, 5%.
And what's the ratio of the dipole interaction?
And to the kinetic energy. Yeah, I mean, it's basically the same. It's few percent. Yeah, it's kind of going, yeah.
You preload density, that's right.
No, it's not about, so the dipolar interaction is d square n, okay? So the density is very high in our case, n is extremely high. The dipolar strength is small compared to the kinetic energy.
The density sets the Fermi energy, so the ratio is very small.
Yes, it's smaller. So the kinetic energy is much larger than the dipole interaction.
It's most 5%.
Yes, yes. But somehow with this type of system, you can increase a lot the density. So I think that was only, I mean, some proof of principle. But I think you can actually go to maybe 10, 15%.
Okay, but if 5% you see. So then the quick question, or the quick question is that when you have dipolar interactions, I mean, we looked at this problem in BCS, the dipole interaction. So you introduce this D-wave component, but it's not too big. So we're really going to have just some kind of crossover physics, not a phase transition that we're expecting, QP wave or QP wave. So the question is, have you guys measured more or less what would be the contribution that the dipole interaction would have in terms of effective scattering, D-wave length?
No. This we have not done. No. So what we have done at the moment, we have produced in the BCS side a long-lived, strongly interacting Fermi gas. That's what we have done at the moment. All the rest will be future plans. So this is what we have done.
Right, but even the measurement of the scattering
Yeah.
parameters, including those things.
Yeah, this is so it's S-wave scattering lens.
Okay, on.
Yeah, because it's two spin states. I mean, actually, we don't know. Nobody knows. We think it might be S, but we don't know.
I think we should discuss the rest in the booster session. Thank
Yeah.
you very much for your nice talk.